Okay, for section 13.4 we have total differentials, and here's the definition for total differentials. All it is simply is a way for us to combine and write the differentials of a function z, which here we have z equals to f of xy, using multiple components. Because of our partial derivatives and because z is a function in space, it has more than one derivative or one differential. So we say that the total differential of z, which is dz, equals to dz dx times dx plus dz dy times dy, where these right here are the partial derivatives of z with respect to x and then with respect to y. So let's take a look at example 1. I want us to find the total differential of the function z equals to 2x sine y minus 3x squared y squared. So dz is going to equal to the partial of z with respect to x, so that's what we have to calculate, plus the partial of z with respect to y and the other part that we have to calculate. Now all we do is plug it in. So dz dx is going to be 2 sine y dy plus, now dz dy, taking the derivative with respect to y, is going to be 2x cosine y minus, now here we've got with respect to y, so x's are constant, so we have 6x squared y dy. And that's it. Let's try another function. W equals 2 x squared plus y squared plus c squared. dw equals 2 dw dx times dx plus dw dy times dy plus dw dz times dz. So calculating these first partials, I have 2x dx plus 2y dy plus 2z dz. Okay, the next section is 13.5, and we've got the chain rule for our partial derivatives. The first one we're going to do is the chain rule with one independent variable, and here is our definition for it. So just take a look at this. If we have w as some function of x and y, where x and y are also functions of some other variable, so in this case x is some function of t and y is also some other function of t, where h and g are differentiable functions of t, then we say that dw dt equals dw dx times dx dt plus dw dy times dy dt. There is a nice little branch diagram that can be used to help you figure out what these partials are supposed to be. If you put your function up at the top, which is your independent variable, and you put the variable that your intermediate variables are written in terms of at the bottom, I'll write x and y over here. Then if you follow the branches, you can see that over here you have dw dx, and over here you have dx dt. Over here on the right you have dw dy, and over here you have dy dt. So if you multiply these two and multiply these two together, you're going to have your dw dt. So let's take a look at an example over here. Let w equals to the inverse tan of y over x, and x is going to equal cosine 3t, y equals sine 5t. So I want to find dw dt. So in this case, dw dx is going to be the derivative of w with respect to x. So this is arctan, so I've got 1 over 1 plus y squared over x squared. Now I still have the chain rule, so the derivative of y over x with respect to x is going to be negative y over x squared. So this is my dw dx. Now I also need dx dt. So notice x over here is in terms of t, so we're going to multiply by a negative 3 sine of 3t. Then I'm going to add to it dw dy. So once again, it's the derivative of the arctan, so 1 over 1 plus y squared over x squared. And then the chain rule, So I need to multiply by the derivative of the inside with respect to y this time. So it's actually only 1 over x. Then I have the derivative of y with respect to t, which is 5 cosine 5t. Now I need to clean this stuff up a little bit, so I can change the signs here, multiply these two together, gives me a y over x squared plus y squared. Then I have the extra 3 sine 3t. Over here on the right hand side, I'm going to multiply by an x on the top and an x on the bottom to give myself an x squared. So when I multiply these two together, I get x over x squared plus y squared. Then I have the extra 5 cosine 5t. Again, putting all of these together once again, and also substituting in for my x's and my y's, I'm going to have 3 sine 5t sine 3t plus 5 cosine 3t cosine 5t all over cosine squared 3t plus sine squared 5t. Let's try one more. Let w equal to x squared y minus y squared, and x equals to sine t and y equals e to the t. So I want to find dw dt. So using our branch diagram, I've got w, my intermediate variables are x and y, and I want to write it in terms of t. So that means I need to have dw dx times dx dt, and then dw dy times dy dt. So dw dx, take the derivative of this function with respect to x, is going to be 2xy. dx dt is cosine t. dw dy now with respect to y is going to be x squared minus 2y. And dy dt is just another e to the t. So we'll simplify this as well as substituting in our x and our y. So I have 2 sine t e to the t cosine t plus sine squared t minus 2e to the t times another e to the t. And you can just clean this up as your final answer and be done. Now I could also do this problem one other way. I want us to rewrite w as a function of t, and then I want us to find dw dt. Now since w equals to x squared y minus y squared, I can think of w of t as sine squared t e to the t minus e to the 2t, and then calculate the derivative of it with respect to time. Now notice just how it's different. This is done in single variable, as in single variable calculus, whereas the other one we used partial derivatives and therefore multivariable calculus. So some of you guys may argue that, wait, this seems a little bit easier, and it may be for this problem, but all of our functions will not always look like this, and this is just sort of to demonstrate the connection between what we're doing with partial derivatives and what you are familiar with in your single variable calculus. Alright, so we've got one last thing, and this is the chain rule for two independent variables, and it's our theorem for it, and it's just extending it one more step. And I again just want to show you how it still works the same way, and how we could even extend it to work for more than two variables, like 3 variables. So let's take a look at this. This is the same thing. We have some function w in terms of x and y, but our intermediate variables x and y are in terms of 2 variables themselves. So notice my branch diagram has an s and a t down here at the bottom. So that simply means that we'll be finding dw ds and a dw dt, 2 separate ones, whether you're dealing with it with respect to s or with respect to t. So as our example, let's take a look at w equals to 2xy, and x is equal to s squared plus t squared, and y equals to s over t. So I want to find dw ds as well as dw dt. Now, so for dw ds, looking at our branch diagram, the first branch on the left-hand side would give us dw dx, and then I need to multiply by dx ds, then I need to multiply by dw dy, and dy ds. So if you take a look, and let's go ahead and figure out what dw dt would be right off the bat. That would be dw dx, but now I want to multiply by dx dt, then I'll have dw dy here times dy dt. Now notice I'm just following along the branches here and over here on the right hand side. So let's plug in our numbers. For dw dx we have 2y, dx ds we have 2s, dw dy is equal to 2x, and dy ds is equal to 1 over t. Putting in our substitutions for x and y and simplifying things out, we have 2 times s over t times 2s plus 2 times s squared plus t squared times 1 over t. Clean all of this stuff up. We have 4s squared over t plus 2 times s squared plus t squared over t, which equals 6s squared plus 2t squared all over t. So let's do the last one over here, dw dt. So we have 2y times 2t plus 2x times negative s over t squared. Be careful here with the derivative of y with respect to t, and substituting in everything that we have. Since x equals to s squared plus t squared, we'll plug that in and simplify. Now we can also extend this to 3 variables, and I'll show you that branch diagram as our very last thing. Let's just write this up. So cleaning this up, it's going to be 2st squared minus 2s cubed all over t squared. So let me just show you the branch diagram. If we had 3 variables, some function w in terms of x, y, and z would mean you have 3 branches, and if x, y, and z were written in terms of s and t, x of st, y of st, and z of st, our branches would be, for example, dw dx, and over here dx ds, or dx dt. Over here we would have dw dy, and either dy ds or dy dt. Then on the right hand side we would have dw dz, and then dz ds or dz dt. So I hope the little branch diagram makes sense and can help you figure out which partials to use when using the chain rule.